before I talk about some of the interesting stuff with parallelization, all that, let's first talk about like the basics. We talked to indentation, right? So this thing looks like Python. It's sexy and beautiful like Python, as we mentioned.
Yep.
Is it a typed language? So what's the role of types?
Yeah, good question. So Python has types. It has strings, it has integers, it has dictionaries, and like all that stuff, but they all live at runtime, right? And so because all those types live at runtime in Python, you don't have to spell them. Python also has like this whole typing thing going on now, and a lot of people use it.
Yeah.
I'm not talking about that. That's kind of a different thing. We can go back to that if you want. But typically the you just say I have a def, and my def takes two parameters. I'm going to call them A and B, and I don't have to write a type. Okay, so that is great, but what that does is that forces what's called a consistent representation. So these things have to be a pointer to an object with the object header, and they all have to look the same. Mm-hmm. And then when you dispatch a method, you go through all the same different paths, no matter what the receiver, whatever that type is. So what Mojo does is it allows you to have more than one kind of type. And so what it does is allows you to say, okay, cool, I have an object, and objects behave like Python does. And so it's fully dynamic, and that's all great. And for many things, classes, like that's all very powerful and very important. But if you want to say, hey, it's an integer and it's 32 bits or it's 64 bits or whatever it is, or it's a floating point value and it's 64 bits, well, then the compiler can take that and it can use that to do way better optimization. And it turns out, again, getting rid of the indirections, that's huge. It means you can get better code completion because you have, because the compiler knows what the type is, and so it knows what operations work on it. And so that's actually pretty huge. And so what Mojo does is it allows you to progressively adopt types into your program. And so you can start, again, it's compatible with Python. And so then you can add however many types you want, wherever you want them. And if you don't want to deal with it, you don't have to deal with it. Right. And so one of our opinions on this is that it's not that types are the right thing or the wrong thing. It's that they're a useful thing.
Well, so it's kind of optional. It's not strict typing. Like, you don't have to specify a type.
Exactly.
Okay, so it's starting from the thing that Python's kind of reaching towards right now with trying to inject types into it.
With a very different approach, but yes. Yeah.
What's the different approach? I'm actually one of the people that have not been using types very much in Python. So
that's okay. Why did you sigh?
It's just, because I know the importance. It's like adults use strict typing. And so I refuse to grow up in that sense. It's a kind of rebellion. But I just know that it probably reduces the amount of errors, even just forget about performance improvements. It probably reduces errors when you do strict typing.
Yeah, so I mean, I think it's interesting if you look at that, right? And the reason I'm giving you a hard time, man, is that there's this cultural norm, this pressure, this like there has to be a right way to do things. Like only grown-ups only do it one way, and if you don't do that, you should feel bad.
Yes,
right. Like some people feel like Python's a guilty pleasure or something, and that's like when it gets serious, I need to go rewrite it. Right?
Yeah, exactly.
Well, I mean, cool. I understand history and I understand kind of where this comes from, but I don't think it has to be a guilty pleasure.
Yeah.
Right. And so if you look at that, you say, why do you have to rewrite it? Well, you have to rewrite it to deploy. Well, why do you want to deploy? Well, you care about performance, or you care about predictability, or you want, a tiny thing on the server that has no dependencies, or, you have objectives that you're trying to attain. So what if Python can achieve those objectives? So if you want types, well, maybe you want types because you want to make sure you're passing in the right thing. Sure, you can add a type. If you don't care, you're prototyping some stuff, you're hacking some things out, you're like pulling some random code off the internet, it should just work, right? And you shouldn't be like pressured. You shouldn't feel bad about doing the right thing or the thing that feels good. Now, if you're in a team, right, you're working at some massive internet company and you have 400 million lines of Python code, well, they may have a house rule that you use types, right? Because it makes it easier for different humans to talk to each other and understand what's going on, and bugs at scale, right? And so there are lots of good reasons why you might want to use types, but that doesn't mean that everybody should use them all the time, right? So what Mojo does is it says, cool, well, allow people to use types, and if you use types, you get nice things out of it, right? You get better performance and things like this, right? But Mojo is a full compatible superset of Python. Right. And so that means it has to work without types. It has to support all the dynamic things, it has to support all the packages, it has to support for comprehension, list comprehensions and things like this, right? And so that starting point, I think, is really important. And I think that again, you can look at why I care so much about this, and there's many different aspects of that. One of which is the world went through a very challenging migration from Python 2 to Python 3. Right. And this migration took many years, and it was very painful for many teams. Right.
Yeah.
And there's a lot of things that went on in that. I'm not an expert in all the details, and I honestly don't want to be. I don't want the world to have to go through that.
Yeah.
Right. And people can ignore Mojo, and if it's not their thing, that's cool. But if they want to use Mojo, I don't want them to have to rewrite all their code.
Yeah. I mean, the superset part is. It's just, I mean, there's so much brilliant stuff here. That definitely is incredible. We'll talk about that.
Yeah.
But first of all, how's the typing implemented differently in Python versus Mojo?
Yeah.
So this heterogeneous flexibility, you said, is differently implemented.
Yeah. So I'm not a full expert in the whole backstory on types in Python. So I'll give you that. I can give you my understanding. My understanding is basically, like many dynamic languages, the ecosystem went through a phase where people went from writing scripts to writing large scale, huge code bases in Python. And at scale, it kind of helps to have types.
Yeah.
People want to be able to reason about interfaces. What do you expect, a string or an int, or like what these basic things, right? And so what the Python community started doing is it started saying, okay, let's have tools on the side. Checker tools, right? That go and like enforce invariance, check for bugs, try to identify things. These are called static analysis tools generally. And so these tools run over your code and try to look for bugs. What ended up happening is there's so many of these things, so many different weird patterns and different approaches on specifying the types and different things going on, that the Python community realized and recognized, hey, there's a thing here. And so what they started to do is they started to standardize the syntax for adding types to Python. Now, one of the challenges that they had is that they're coming from kind of this fragmented world where there's lots of different tools, they have different trade-offs and interpretations, and the types mean different things. And so if you look at types in Python, according to the Python spec, the types are ignored. Right. So according to the Python spec, you can write pretty much anything in a type position. Okay. And you can write any expression. Okay. Now, that's beautiful because you can extend it. You can do cool things. You can build your own tools. You can build your own house linter or something like that, right? But it's also a problem because any existing Python program may be using different tools and they have different interpretations. And so if you adopt somebody's package into your ecosystem, try to run the tool you prefer, it may throw out tons of weird errors and warnings and problems just because it's incompatible with how these things work. Also, because they're added late and they're not checked by the Python interpreter, it's always kind of more of a hint than it is a requirement. Also, the CPython implementation can't use them for performance. And so it's really...
I mean, that's the big one, right? So you can't utilize for the compilation, for the just-in-time compilation. Okay.
Yep, exactly. And this all comes back to the design principle of they're kind of hints. They're kind of, the definition's a little bit murky. It's unclear exactly the interpretation in a bunch of cases. And so because of that, you can't actually... even if you want to, it's really difficult to use them to say, like, it is going to be an int, and if it's not, it's a problem, right? A lot of code would break if you did that. So in Mojo, right, so you can still use those kind of type annotations, it's fine. But in Mojo, if you declare a type and you use it, then it means it is going to be that type. And the compiler helps you check that and enforce it, and it's safe. And it's not a, like, best effort hint kind of a thing.
So if you try to shove a string type thing into an integer,
you get an error from the compiler.
From the compile time. Nice. Okay, what kind of basic types are there?
Yeah, so Mojo is pretty hardcore in terms of what it tries to do in the language, which is, the philosophy there is that we, again, if you look at Python, right, Python's a beautiful language because it's so extensible, right? And so all of the different things in Python, like for loops and plus and like all these things, can be accessed through these underbar methods. Okay, so you have to say, okay, if I make something that is super fast, I can go all the way down to the metal. Why do I need to have integers built into the language? Right, and so what Mojo does is it says, okay, well, we can have this notion of structs. So you have classes in Python. Now you can have structs. Classes are dynamic. Structs are static. Cool. We can get high performance. We can write C++ kind of code with structs if you want. These things mix and work beautifully together. But what that means is that you can go and implement strings and ints and floats and arrays and all that kind of stuff in the language, right? And so that's really cool because to me as a idealizing compiler language type of person, what I want to do is I want to get magic out of the compiler
Mhm.
and put it in the libraries. Because if somebody can, if we can build an integer that's beautiful and it has an amazing API and it does all the things you'd expect an integer to do, but you don't like it, maybe you want a big integer, maybe you want a like sideways integer. I don't know, like what all the space of integers are. Then you can do that, and it's not a second class citizen. And so if you look at certain other languages like C++, one I also love and use a lot, int is hard coded in the language, but complex is not.
Mhm.
And so isn't it kind of weird that you have this std complex class,
Mhm.
but you have int, and complex tries to look like a natural numeric type and things like this. But integers and floating point have these like special promotion rules and other things like that are magic, and they're hacked into the compiler. And because of that, you can't actually make something that works like the built-in types.
Mhm.
And so,
Is there something provided as a standard? Because because it's AI first, numerical types are so important here.
mhm.
So is there something like a nice standard implementation of integer and floats?
Yeah, so we're still building all that stuff out. So we provide integers and floats and all that kind of stuff. We also provide like buffers and tensors and things like that you'd expect in an ML context. Honestly, we need to keep designing and redesigning and working with the community to build that out and make that better. That's not our strength right now. Give us 6 months or a year, and I think it'll be way better. But the power of putting it in the library means that we can have teams of experts that aren't compiler engineers that can help us design and refine and drive this forward.
So one of the exciting things we should mention here is that this is new and fresh. This cake is unbaked. It's almost baked. You can tell it's delicious, but it's not fully ready to be consumed.
Yep, that's very fair. It is very useful, but it's very useful if you're a super low level programmer right now. And what we're doing is we're working our way up the stack. And so the way I would look at Mojo today in May in 2023 is that it's like a 0.1. So I think that a year from now, it's going to be way more interesting to a variety of people. But what we're doing is we decide to release it early so that people can get access to it and play with it. And we can build it with the community. We have a big roadmap, fully published, being transparent about this, and a lot of people are involved in this stuff. And so what we're doing is we're really optimizing for building this thing the right way.
Mhm.
And building it the right way is kind of interesting working with the community because everybody wants it yesterday. And so sometimes it's kind of, there's some dynamics there, but
Yeah,
I think it's the right thing.
So there's a Discord also. So the dynamics is pretty interesting.
Yeah.
Sometimes the community probably can be very chaotic and introduce a lot of stress. Guido famously quit over the stress of the walrus operator. I mean,
Yeah,
that broke.
Maybe that straw that broke the camel's back.
Yeah, exactly. And so like it could be very stressful to develop. But can you just tangent upon a tangent? Is it stressful to work through the design of various features here, given that the community is so richly involved?
Well, so I've been doing open development and community stuff for decades now. Somehow this has happened to me. So I've learned some tricks, but the thing that always gets me is I want to make people happy,
Mhm.
right? And so this is maybe not all people all happy all the time, but
Yeah.
generally I want people to be happy, right? And so the challenge is that again we're tapping into some deep-seated long tensions and pressures, both in the Python world, but also in the AI world and the hardware world and things like this. And so people just want us to move faster, right? And so again, our decision was let's release this early. Let's get people used to it or access to it and play with it, and like let's build it in the open, which we could have had the language monk sitting in the cloister up on the hilltop, like beavering away trying to build something. But in my experience, you get something that's way better if you work with the community, right? And so yes, it can be frustrating, it can be challenging for lots of people involved. And if you mentioned our Discord, we have over 10,000 people on the Discord, 11,000 people or something. Keep in mind, we released Mojo like 2 weeks ago.
Yeah.
So
it's very active.
So it's very cool. But what that means is that 10, 11,000 people all will want something different, right? And so what we've done is we've tried to say, okay, cool, here's our roadmap. Here, and the roadmap isn't completely arbitrary. It's based on here's the logical order in which to build these features or add these capabilities and things like that. And what we've done is we've spun really fast on like bug fixes, and so we actually have very few bugs, which is cool. I mean, actually for a project in the state. But then what we're doing is we're dropping in features very deliberately.
I mean, this is fun to watch because you got the two gigantic communities of like hardware, like systems engineers, and then you have the machine learning Python people that are like higher level.
Yeah,
and it's just two like army like
they've been at war. Yeah, they've been at war, right? And so here's
like
a
a Tolkien
test.
novel or something. Okay,
Well, so here's the test. And again, like it's super funny for something that's only been out for 2 weeks, right? People are so impatient, right? But okay, cool. Let's fast forward a year.
Mhm.
Like in a year's time, Mojo will be actually quite amazing and solve tons of problems and be very good. People still have these problems,
Mhm.
right? And so you look at this and you say, and the way I look at this at least is to say, okay, well, we're solving big, long-standing problems. To me, again, working on many different problems, I want to make sure we do it right. Right. There's like a responsibility you feel because if you mess it up, right, there's very few opportunities to do projects like this and have them really have impact on the world. If we do it right, then maybe we can take those feuding armies and actually heal some of those wounds.
Yeah, this
Right?
is like this feels like a speech by George Washington or Abraham Lincoln or something.
And you look at this and it's like, okay, well, how different are we?
Yeah,
We all want beautiful things. We all want something that's nice. We all want to be able to work together. We all want our stuff to be used, right? And so if we can help heal that, now I'm not optimistic that all people will use Mojo and they'll stop using C++. Like that's not my goal, right? But if we can heal some of that, I think that'd be pretty cool.
yeah,
That'd be
and
nice.
we start by putting the people who like braces into the gulag. No,
So there are proposals for adding braces to Mojo, and we just
interesting.
we tell them no.
Okay. Politely. Yeah. Anyway, so there's a lot of amazing features on the roadmap and those already implemented. It'd be awesome if I could just ask you a few things.
Yeah,
so,
go for it.
So the other performance improvement comes from immutability. So what's this var and this let thing that we got going on?
Well,
and what's immutability?
Yeah, so one of the things that is useful, and it's not always required, but it's useful, is knowing whether something can change out from underneath you, right? And so in Python, you have a pointer to an array, right? And so you pass that pointer to an array around to things. If you pass into a function, they may take that and scroll it away in some other data structure.
Mhm.
And so you get your array back and you go to use it, and now somebody else is like putting stuff in your array.
Yeah.
How do you reason about that? It gets to be very complicated and leads to lots of bugs, right? And so one of the things that, again, this is not something Mojo forces on you, but something that Mojo enables is a thing called value semantics. And what value semantics do is they take collections like arrays, like dictionaries, also tensors and strings and things like this that are much higher level and make them behave like proper values. And so it makes it look like if you pass these things around, you get a logical copy of all the data. Mm-hmm. And so if I pass you an array, it's your array. You can go do what you want to it. You're not going to hurt my array. Now, that is an interesting and very powerful design principle. It defines away a ton of bugs. You have to be careful to implement it in an efficient way.
Yeah, is there a performance hit that's significant?
Generally not, if you implement it the right way, but it requires a lot of very low level getting the language right bits.
I assume there'd be a huge performance hit because it's a really the benefit is really nice because you don't get into these
absolutely. Well, the trick is you can't do copies, so you have to provide the behavior of copying without doing the copy.
Yeah, how do you do that? How do you do that?
It's not magic. It's just it's actually pretty cool. Well, so first, before we talk about how that works, let's talk about how it works in Python, right? So in Python, you define a person class, or maybe person class is a bad idea. You define a database class, right? Mm-hmm. And a database class has an array of records, something like that, right? And so the problem is that if you pass in a record or a class instance into the database, it'll take a hold of that object, and then it assumes it has it. Mm-hmm. And if you're passing an object in, you have to know that that database is going to take it, and therefore you shouldn't change it after you put it in the database, right? This is
you just kind of have to know that.
You just have to kind of know that, right? And so you roll out version 1 of the database. You just kind of have to know that. Of course, Lex uses his own database, right?
Yeah.
Right? Because you built it. You understand how this works, right? Somebody else joins the team. They don't know this.
Yes.
Right? And so now they suddenly get bugs. You're having to maintain the database. You shake your fist.
Mhm.
You argue the 10th time this happens, you're like, okay, we have to do something different, right? And so what you do is you go change your Python code and you change your database class to copy the record
Mhm.
every time you add it. And so what ends up happening is you say, okay, I will do what's called a defensive copy inside the database. And then that way, if somebody passes something in, I will have my own copy of it and they can go do whatever and they're not going to break my thing.
Mhm.
Okay. This is usually the two design patterns. If you look in PyTorch, for example, this is cloning a tensor.
Mhm.
Like there's a specific thing and you have to know where to call it. And if you don't call it in the right place, you get these bugs. And
Mhm.
this is state of the art, right? So a different approach, so it's used in many languages, so I've worked with it in Swift, is you say, okay, well, let's provide value semantics. And so we want to provide the view that you get a logically independent copy,
Mhm.
but we want to do that lazily. And so what we do is you say, okay, if you pass something into a function, it doesn't actually make a copy. What it actually does is it just increments a reference to it. And if you pass it around, you stick it in your database, it can go in the database, you own it, and then you come back out of the stack, nobody's copied anything. You come back out of the stack, and then the caller lets go of it. Well, then you've just handed it off to the database, you've transferred it, and there's no copies made. Now, on the other hand, if you know your coworker goes and hands you a record and you pass it in, you stick it in the database, and then you go to town and you start modifying it, what happens is you get a copy lazily on demand. And so what this does is gives you copies only when you need them. And it also, so it defines away the bugs, but it also generally reduces the number of copies in practice. And so
But
it's,
the implementation details are tricky here. I assume with
yeah.
the
So this is, yes.
something with reference counting, but to make it performant across a number of different kinds of objects.
Yeah. Well, so you need a couple of things. And so there's many, so this concept has existed in many different worlds. And so it's again, it's not novel research at all, right? The magic is getting the design right so that you can do this in a reasonable way, right? And so there's a number of components that go into this. One is when you're passing around, so we're talking about Python and reference counting at the expense of doing that. When you're passing values around, you don't want to do extra reference counting for no good reason.
Mm-hmm.
And so you have to make sure that you're efficient and you transfer ownership instead of duplicating references and things like that, which is a very low level problem. You also have to adopt this and you have to build these data structures. And so if you say, Mojo has to be compatible with Python. So of course the default list is a reference semantic list that works the way you'd expect in Python,
Mm-hmm.
but then you have to design a value semantic list. And so you just have to implement that and then you implement the logic within. And so the role of the language here is to provide all the low level hooks that allow the author of the type to be able to get and express this behavior without forcing it into all cases or hard coding this into the language itself.
But there's ownership, so you're constantly transferring, you're tracking who owns the thing.
Yes. And so there's a whole system called ownership. And so this is related to work done in the Rust community.
Mm-hmm.
Also, the Swift community has done a bunch of work, and there's a bunch of different other languages that have all kind of C++ actually has copy constructors and destructors and things like that. And so, and I mean, C++ has everything. So it has move constructors and has like this whole world of things. And so this is a body of work that's kind of been developing for many, many years now. And so Mojo takes some of the best ideas out of all these systems and then remixes it in a nice way so that you get the power of something like the Rust programming language, but you don't have to deal with it when you don't want to, which is a major thing in terms of teaching and learning and being able to use and scale these systems.
How does that play with argument conventions? What are they? Why are they important? How does the value semantics, how does the transfer ownership work with the arguments when they're passed into functions?
Yeah, so if you go deep into systems programming land, so this isn't, again, this is not something for everybody, but if you go deep into systems programming land, what you encounter is you encounter these types that get weird. So if you're used to Python, you think about everything, I can just copy it around, I can go change it and mutate it and do these things, and it's all cool. If you get into systems programming land, you get into these things like I have an atomic number, or I have a mutex, or I have a uniquely owned database handle, things like this, right? So these types you can't necessarily copy. Sometimes you can't necessarily even move them to a different address. And so what Mojo allows you to do is it allows you to express, hey, I don't want to get a copy of this thing. I want to actually just get a reference to it. And by doing that, what you can say is you can say, okay, if I'm defining something weird, like a atomic number or something, it's like it has to be. So an atomic number is a an area in memory that multiple threads can access at a time without without locks, right? And so like the definition of an atomic number is multiple different things have to be poking it. Therefore, they have to agree on where it is, right? And so you can't just like move it out from underneath one because it kind of breaks what it means. And so that's an example of a type that you can't copy, you can't move it. Like once you create it, it has to be where it was, right? Now, if you look at many other examples, like a database handle, right? So, okay, well, what happens? How do you copy a database handle? Do you copy the whole database? That's not something you necessarily want to do. There's a lot of types like that where you want to be able to say that they are uniquely owned. So there's always one of this thing, or if I create a thing, I don't copy it. And so what Mojo allows you to do is it allows you to say, hey, I want to pass around a reference to this thing without copying it. And so it has borrowed conventions. So you can say, you can use it, but you don't get to change it. You can pass it by mutable reference. And so if you do that, then you get a reference to it, but you can change it. And so it manages all that kind of stuff.
So it's just a really nice implementation of like C++ has, the different kinds of pointers.
Yeah, it has pointers.
Smart, different kinds of implementations of smart pointers that you can explicitly define. This allows you, but you're saying that's more like the weird case versus the common case.
Well, it depends on where. I mean, I don't think I'm a normal person, so I mean, I'm not one to call other people weird.
Yeah.
But if you talk to a typical Python programmer, you're typically not thinking about this, right? This is a lower level of abstraction. Now, if you talk to a C++ programmer, certainly if you talk to a Rust programmer, again, they're not weird, they're delightful. Like these are all good people, right? Those folks will think about all the time, right? And so I look at this as there's a spectrum between very deep, low-level systems. I'm going to go poke the bits and care about how they're laid out in memory, all the way up to application and scripting and other things like this. And so it's not that anybody's right or wrong. It's about how do we build one system that scales.
By the way, the idea of an atomic number has been something that always brought me deep happiness, because the flip side of that, the idea that threads can just modify stuff asynchronously, just the whole idea of concurrent programming is a source of infinite stress for me.
Well, so this is where you jump into again, you zoom out and get out of programming languages or compilers and you just look at what the industry has done. My mind is constantly blown by this, right? And you look at what, Moore's Law. Moore's Law is this idea that like computers for a long time, single thread performance just got faster and faster and faster and faster for free. But then physics and other things intervened, and power consumption, like other things started to matter. And so what ended up happening is we went from single core computers to multi-core. Then we went to accelerators, right? And this trend towards specialization of hardware is only going to continue. And so for years, us programming language nerds and compiler people have been saying, okay, well, how do we tackle multi-core, right? For a while, it was like, multi-core is the future. We have to get on top of this thing. And then it was multi-core is the default. What are we doing with this thing? And then it's like, there's chips with hundreds of cores in them. what happened, right?
Yeah.
And so I'm super inspired by the fact that, in the face of this, those machine learning people invented this idea of a tensor, right? And what is a tensor? A tensor is an arithmetic and algebraic concept. It's like an abstraction around a gigantic parallelizable data set, right? And because of that, and because of things like TensorFlow and PyTorch, we're able to say, okay, we'll express the math of the system. This enables you to do automatic differentiation. This enables you to do like all these cool things, and it's an abstract representation. Well, because you have that abstract representation, you can now map it onto these parallel machines without having to control. Okay, put that byte here, put that byte there, put that byte there, and this has enabled an explosion in terms of AI, compute, accelerators, like all the stuff. And so that's super, super exciting.